Hello students, my name is Mr. Low. Today I'm going to give you a short lesson on this topic called electrolytic cell. Now, in an electrolytic cell, usually you have a glucose solution. You have your cathode, anode, connected by wire towards your battery. So the most important feature, right, of an electrolytic cell is the battery. Now, the battery, right, in simple notation, is a long line representing the plus and a short line representing the minus. So the most important part of electrolytic cell is the battery. Now, why do you need the battery? Because the battery is the driving force for all non-spontaneous reaction to occur in an electrolytic cell. So the battery is the most important component in an electrolytic cell. You see the battery, you know this is electrolytic. Okay? Now, in an electrolytic cell, cathode attracts cation. Cation is plus, cathode is minus. Cathode is where reduction occurs. Anode attracts anion. Anion is minus, anode is plus. Anode is where oxidation occurs. So this is a quick overview of what electrolytic cell is all about. Okay, part one. Now, part two. Let's look at the selective discharge of ions at electrode. If I have a molten state, there's only one cation, one anion. So things are pretty simple. At the cathode, my cation is attracted there. Cathode is where reduction occurs. So my sodium plus is attracted to the cathode. You will get reduced to form sodium liquid if I'm electrolyzing molten sodium chloride. Now, my anode will attract the anion chloride. Anode is where oxidation occurs. So my chloride will get oxidized to form chlorine gas. So this is molten state. Pretty simple. There's only one cation, one anion, that's all. Okay, so that's part one. Second, now if I'm electrolyzing an aqueous solution, things become a bit more complicated. Because other than the respective ions, I need to consider water molecule as well. Now, ultimately, right, whether the ions get reduced or oxidized, or whether the water gets reduced or oxidized, we're going to look at three factors: electric potential, concentration, and nature of the electrode. And please take note, in an aqueous solution, please do not consider H plus or OH minus, unless your H plus OH minus is from a strong acid or a strong base. Okay, now why not? Now, in acid-base equilibrium, H plus equals to OH minus. They have a concentration of 1.0 times 10 to the power minus 7 mole per dm cube. Water has a concentration of 55.6 mole per dm cube. So from this value, you can see water is a lot more concentrated than H plus OH minus. So if you're talking about aqueous solution, you only consider water. Do not talk about H plus OH minus, unless you're talking about strong acid or strong base. Okay, I hope I make myself clear. Now let's look at the first factor, electric potential. At the cathode, let's say I have these three species that want to get reduced. I have my H plus, copper 2 plus, which are my cations attracted to the cathode. Aqueous solution also have some water there. Now at a cathode, you can only choose one to get reduced. Who do you choose? You choose the most positive E0 reduction to get reduced first. So among the three species, your copper 2 plus has the most positive E0 reduction potential. So copper 2 plus is reduced preferentially over H plus water. To start. Understand? Now, at the cathode, I need to ignore all the group 1, group 2, group 13 metal cation if you are talking about aqueous solution. Reason being, in the presence of water, all these metal cations will never get reduced because water is always in front of them. Now, what do I mean by water is in front of them? Sodium plus to sodium, its E reduction is minus 2.71. Water gets reduced to form H2, its E reduction is minus 0.83. Remember, at the cathode, we choose the most positive E value to get reduced first. So your water is reduced preferentially over your sodium plus. So as long as you have aqueous solution and there's water, all this group 1, group 2, group 13 metal cation, they will never get a chance to be reduced because water is always in front of them. Okay, so that's cathode. Now, at the A node, I have hydroxide. Let's say I have some chloride and I have some water from an aqueous solution. You can only choose one to get oxidized because A node is where oxidation occurs. This time round at the A node, I choose the least positive E naught reduction value to get oxidized first. So among the three of them, hydroxide has the least positive E naught reduction potential. So hydroxide is oxidized preferentially over the other two. Okay. Now at the A node, right, there are also two ions I need to ignore. One of them is sulfate, the other one is nitrate. Now, why do we ignore them? Sulfate, the E reduction is plus 2.01. Water is plus 1.23. Remember, at the A node, we choose the least positive one to get oxidized. So again, as long as there's water, water will be oxidized preferentially over sulfate. So sulfate will never get oxidized at the A node. Good. Now, nitrate will also not get oxidized at the A node at all. Why? Now, if you look at the data booklet, your nitrate, these are the three equations in the data booklet. If you look carefully, nitrate appears on the left-hand side of the equation, which means that nitrate can only undergo reduction. They will never get oxidized. So that is why at the A node, whenever you see sulfate and nitrate, you can ignore them straight away. Okay? So in summary, at the cathode in an aqueous solution, you ignore all the group 1, group 2, group 13 metal cation ion. They will never get reduced because water is always in front of them. So whatever that is left, you choose the most positive one to get reduced at the cathode. At the A node, you ignore your sulfate and your nitrate because they will never get oxidized. So whatever species that's left at the A node, you choose the least positive one to get oxidized. So that's factor number 1, electric potential. Okay. Okay. Now let's look at the second factor, this factor called concentration. Ions at higher concentration, they can be discharged in preference even though their E naught reduction potential is not as favorable. Okay, what do I mean by that? Now let's say I'm going to electrolyze sodium chloride. There are two ions, sodium plus chloride. At the cathode, cathode attracts cation ion, my sodium plus is there. I also have water because we're talking about aqueous sodium chloride. At the A node attracts N ion, my chloride is there, my water is also there because this is an aqueous solution. Okay? Now let's talk about dilute sodium chloride first. At the cathode, we choose the more positive one to get reduced. So at the cathode, right, your water is reduced preferentially over your sodium plus because minus 0.83 is more positive than minus 2.71. So for a dilute sodium chloride at the cathode, you form H2 gas. Now at the A node for dilute sodium chloride, at the A node, we choose the least positive one to get oxidized. So plus 1.23 is less positive than plus 1.36. So for dilute sodium chloride, water is oxidized preferentially over your chloride. Yeah? So this was dilute sodium chloride. Now what if we have concentrated sodium chloride? Now for con sodium chloride, I need to talk a bit about LCP, the Chatelier's principle. Now let's look at the cathode first. If I'm using con sodium chloride, it means that this time round, my sodium plus concentration has gone up. When sodium plus concentration goes up, by the Chatelier's principle, the position of equilibrium is going to shift forward. When equilibrium shifts forward, your E value becomes bigger. Bigger means it becomes more positive. So as your equilibrium keeps on shifting to the right, this value becomes more and more positive. Now, first, you take note. The difference between these two values is very big. Okay, minus 2.71, minus 0.83, the difference is very big. So even though your first equilibrium, this equilibrium is shifting forward, and this value is getting more and more positive, it will never become more positive than minus 0.83 because the difference between the two values is too big. So whether you electrolyze dilute sodium chloride or con sodium chloride, at the cathode, it is always water that gets reduced to form H2 gas. Or because the difference between these two values is too big. So concentration plays no part. Okay. Now, how about the anode? Okay, first up, if you look at the anode, right, the difference between these two values is very small. It's only a mere 0.13, that's all. So I'm using corn sodium chloride. So my chloride concentration has gone up. By the Chatelier's principle, my equilibrium is now going to shift to the left. When I shift to the left, this E value will start to drop. Drop means become less positive. Now, because the difference between these two values is very small, this plus 1.36, as it starts to become less positive or drop, there's a high chance that it can drop below plus 1.23. Hence, chloride will be chosen to be oxidized at the anode instead of water. And this is indeed the case for concentrated sodium chloride. So for corn sodium chloride, your chloride is oxidized preferentially over your water to form chlorine gas. Understand? So this concentration factor, right, affects your anode because the difference between these two values is actually very small. So in conclusion, concentration factor, right, will usually only come into play when the difference between the E value is actually very small. Okay? So this is the second factor. The last factor we look at is this thing called the nature of the electrode. Most electrodes that you use in electrochem, they are inert. So there are two common inert electrodes, platinum or graphite. Other than platinum or graphite, all other electrodes that you use, they are normally reactive electrodes. Now, electrodes must be made of metals. Metals must undergo oxidation. So when you change from an inert electrode to a reactive electrode, the only difference will lie at the anode. It will not affect the cathode. Why? Because anode is where oxidation occurs. And metals can only get oxidized, they cannot get reduced. Follow me? Okay, if not, let me give you an example. I'm going to electrolyze aqueous copper 2 sulfate. At the cathode, remember, cathode attracts cation ion. Cathode will attract my copper 2 plus. Aqueous, I have water. If I use an inert platinum electrode at the cathode, I choose the more positive one to more positive value to get reduced. So my copper 2 plus is reduced preferentially over my water. So this is the equation you get at the cathode if you use platinum. If I change my platinum to a reactive copper electrode, at the cathode, it is still copper 2 plus getting reduced to copper solid. Understand? Because your copper electrode, right, can only get oxidized. It cannot get reduced. So cathode is where reduction occurs. So at the cathode, whether you use an inert or a reactive electrode, it makes no diff to your reaction. Okay, I hope you understand now. Now, how about the anode? Now, at the anode, I have my N-ion sulfate, I have my water. So let's say we talk about inert electrode first, platinum. Now, if you have a platinum electrode, you only consider equation 1 and 2. So at the inert platinum electrode, it can only be water getting oxidized or sulfate getting oxidized. At the anode, we choose the less positive one to get oxidized. So if I use platinum electrode, water is oxidized over your sulfate. Okay? If I change my platinum to a copper electrode, copper is a metal, copper is reactive. So what can happen to copper? It can get oxidized. So this time around, I need to consider equation 1, 2, and 3. Understand? At the anode, we choose the least positive one to get oxidized. So this time around, rather than water, copper is the one that will get oxidized preferentially over the other two. So you get copper oxidizing to copper 2 plus. So all in all, when you use a reactive electrode, it will only affect the reaction at the anode. Why? Because electrodes must be made up of metals to conduct electricity. And metals can only get oxidized, they cannot get reduced. So if you change from an inert electrode to a reactive electrode, the only difference will lie at the anode. There's no difference to the cathode, that's all. So this is all I have for you in this short lesson to show you in electrolysis, right? Who gets reduced, who gets oxidized, and how do you choose? Okay, I hope you find this lesson useful for you. Okay, thank you, and I'll see you soon. Bye-bye.